So I'm Aaron Roth, and this is Natalie and Ira, and we're going to tell you for the next 2 hours about calibration, decisions, collaboration, and learning. So, here we are at ICML. We should talk about machine learning. Machine learning, as I'm given to understand, is about making predictions. And the native language of predictions is often probability. So for example, given some context X, like features about an example, we might want to predict something like the probability that an image depicts a cat, or the probability that a patient will develop sepsis sometime in the next 18 hours, or maybe the probability that the next word in some block of text is slept. But given that we're sort of in the business of predicting probabilities, sort of just at the very start of the tutorial, I want to take a moment to take a step back and just like reflect a little bit on what that means. Like, how should we think about probabilistic forecasts? And there's an easy kind of probability that you've been probably asked many questions about if you've taken like an intro probability class. Here's an example of that easy kind of probability. What's the probability that if I flip a fair coin 16 times, I get exactly 9 heads? Oh, I was supposed to give the guy in the back a thumbs up, so he starts recording. Okay, so, this kind of probability is easy and nice for 2 reasons. There's 2 ways you can think about sort of coming to an answer to this question. The first is just that we've got like a terrific, simple, clean mathematical model that happens to map very well onto reality, in which we can tractably just compute the answer to this question in closed form. We can model a coin flip as a Bernoulli random variable, just sit down and compute the answer. And the nice thing is that, this is an experiment we can actually conduct in principle. Like, we can just lock ourselves in our room with a coin. We can flip it a bunch of times. We can count things. And, kind of like the miracle of this setup is that the number we get from computing the answer in closed form, it's the same as the number we will converge to if we conduct the experiment for long enough. But, most probabilities aren't this nice. So just to give you an example, another kind of question you could ask is, what's the probability that J.D. Vance will win the 2028 US presidential election? And this is a probability that people ask. Here's a screenshot from Polymarket a few weeks ago that purports to give an answer, 15%. Okay, so what does that mean? What does it mean that there's a 15% chance that J.D. Vance wins the 2028 election? I mean, maybe, right? If you've had enough to drink, you could posit a probabilistic model of the universe in which this at least makes sense. Maybe if I was able to rewind time until now and then run it forwards over and over again until the 2028 election, somehow J.D. Vance would win in 15% of those cases. But unlike the coin flipping example, certainly we don't have a model, an analytic model of probability that would let us compute the answer to this question in any believable way. And we also have no way to actually conduct this experiment. Even if you believe that the universe is inherently probabilistic, it's not an experiment we can conduct. So, for probabilities like this, it's much more difficult to think about what to do with them. And I would claim that for most of the things we actually want to predict in machine learning, even though we're using the language of probability, we're much closer to the second kind of example than to the first kind. We're not in a sort of scenario where we can either think about computing the answer in closed form or conducting the experiment even in principle. So for example, if I ask you, what's the probability of the next token, if I ask you, what's the probability of the next token given 50 pages of text? There's no extant texts that have the same 50-page prefix. There's either one of these or 0. So there's no clean probability space that I can, sit down and count things in. And of course I can't compute the answer in closed form. if I ask you what's the probability that some patient, Alice, develops sepsis in the next 12 hours, well, if I'm doing my job and collecting a rich enough set of measurements of Alice, I've never seen any other patient before who has exactly the same medical history and exactly the same set of readings as Alice. It's going to happen or it's not. There's no clean probability space over which I can sort of pose this as like a well-defined probabilistic question. If I ask what's the probability of rain in Seoul tomorrow, okay, probably pretty likely, but there's no 2 days with exactly the same atmospheric readings, so like it's not totally clear how we would check whether any particular forecast was correct or not. Okay, like this kind of thing comes up all the time. And so, like the issue is that in general, because of this, there's no way to verify the correctness of probabilistic forecasts of individual probabilities like this, things that in principle only happen once. It's like not totally clear they even make sense philosophically. There's, by the way, like an enormous literature in the philosophy of science worrying about exactly this problem. It's called the reference class problem, and you can have fun reading about it. So, like this is the starting point. Like we can't be sure we've learned true probabilities or even whether those make sense for these kinds of events that we want to be able to predict using the language of probability theory, events that in principle only happen once. And so the sort of overarching philosophy of the line of work that we're talking about in this tutorial is that what we should do is we should say, well, what are the properties of true probabilities, if we could actually have them, that actually makes them useful for whatever it is we want to do with them downstream? Like, what do we want to do with these probabilities? Let's think about what we need for that particular task. And maybe we can learn numbers that have those properties, despite the fact that we can't learn real probabilities. Okay, so we're like the goal of this entire tutorial is to talk about how to learn numbers that are sufficiently like probabilities so that we have strong guarantees for the downstream tasks that we'd like to use these predictions for. Okay, so like, what can we do in machine learning in general? We can always measure averages, and essentially averages are the only thing we can measure. So for example, given like a subset, given a data set, say, of patients, we can ask, what's the average outcome? Like what fraction of them are gonna develop sepsis in the next 12 hours? We can ask, what's the average prediction error of our model? And by the way, when we can measure something, we can generally optimize for it. So that's why empirical risk minimization will generally, minimize population level prediction error. We can measure and optimize for other things, not just error. We can measure for bias. But like, we're not limited to just computing and optimizing for error on average over the whole population. We do have to sort of limit ourselves to averages, but we can take averages over different subsets. So for example, we could ask what's the error on this subset of patients, so we could optimize for it. We could ask what's the error on this other subset of patients, we could optimize for it. And as soon as you start talking about measuring and optimizing for notions of error, not on the whole population, but on different subsets, you might start wondering, like, are we just kind of like, getting ourselves into the same trouble we started with? Like, if I design the subsets to be so limited that they contain only a single patient, then we're again back to this problem of individual probabilities. So we're obviously not going to be able to optimize for or even measure anything on subsets that are too small. But fortunately, for all the kinds of guarantees we're going to see today, we're not going to have to do that. So, we'll see this cartoon a couple of times during the tutorial, but one picture I want you to have in your mind is, that there's like two worlds out there. One is the real world. The real world is sort of complicated and messy. There's features, there's labels. We're trying to learn the relationship between the features and the labels in the real world, but we might not have gotten it right. We're going to come up with some model that tries to, produce what purport to be probabilities for the outcome given features. And we're going to think about this other world that later in the talk we'll call optimistica. In the other world, we're just going to pretend that our model is right. That when our model, say, predicts that a patient has a 20% chance of getting sepsis in the next 12 hours, that God really does flip a coin that has bias 20% and like, the probabilistic meaning of our predictions is correct. And the point is, anything we would have wanted to do with probabilities is going to work out great in Optimistica. In Optimistica, our forecasts are probabilities. And our goal will be to design models such that with respect to those statistics that matter for the thing that we're doing, you can't tell which of these two worlds we're in, which will mean that things work great in the real world as well. And like the one trick that we're going to just apply over and over again, you should think of as just like clever debiasing. Like we're just going to ask for our model to be statistically unbiased, not just overall, but on different subsets and different weightings of the input space, and everything is going to follow from that. So, among the things we'll see how to use this to give probabilities that are interpretable. We should be able to say, look, the model predicts that you've only got 0.05% chance of developing sepsis in the next 12 hours, and if the patient asks, what does this mean for me, like we should be able to give them a good answer, right? We should be able to say something about the decision-making process that follows from the forecasts that we're making, right? If we say, okay, well, given the model's predictions, like we'd better treat you for antibiotics. Again, we should be able to translate that into like some decision theoretic guarantee for the patient. There should be some sense in which it is actually a good idea to produce those predictions, to follow the sort of actions that follow from those predictions. We'll see ways to learn collaboratively. If we have sort of two entities, say like a human being and an AI, who have just like different observations that they can't easily communicate directly to one another, they should be able to sort of speak in some common language, like the language of probability, and come to decisions that are better than either of them could have obtained alone. Okay, these are the three applications we're going to see in the tutorial. And just as like a cherry on top, all of this is going to work on top of your favorite existing machine learning pipeline. So, we're going to describe simple methods, and we're not saying like, stop training like large models, use our simple methods. No, the simple methods work on top of your favorite large model. They will endow they'll sort of post-process the predictions your favorite large model is already producing to have all of these nice guarantees. And on top of that, everything we're going to do is only going to be accuracy improving. Nothing's going to harm accuracy. Okay, so there's no sort of hard trade-offs here. Okay, so again, overarching goal, we're going to define a collection of simple empirical tests that real probabilities would pass, but unlike real probabilities, we can actually audit and in fact enforce these from data. We're going to learn predictors that pass these tests from data, and we're going to choose the tests so that any predictor that passes these tests, real probabilities would, but also the things that we learn, are sufficient for what our downstream applications are. Okay, and so, the roadmap of the tutorial sort of has three parts. In the first part, I'm going to tell you about this simple hierarchy of tests. So we'll sort of learn the language for asking for predictors that satisfy these things that you want, and I'll show you a simple algorithm that can obtain them even in sort of challenging settings. Then Natalie's going to tell you about how to use predictors that pass the right set of tests to endow any downstream application, a downstream decision-making application you have coming from these probabilities with strong utility theoretic guarantees. And finally, Ira's going to tell you how to use the same framework to solve a collaborative learning problem, to allow for, say, a short conversation between an AI and a human being to come to decisions that get the complementary benefits of both. Okay, so let's get started. I want to tell you about calibration, which you should think of as, maybe like the lowest level of the hierarchy that we're going to talk about today, like the very simplest thing you could ask from your predictions. So what is calibration? So, suppose I'm a dilettante doctor. I'm not a real doctor. I just think that predicting sepsis might be fun, and I do it once. I walk into a hospital, and before they kick me out, I'm like, that guy over there, I think he's got a 70% chance of developing sepsis in the next 12 hours. Then they kick me out. I never make another prediction again. Say the guy develops sepsis. Like, was my prediction good? Like, should I be a real doctor? Like, did I do a good job? Like, maybe I'm cut out for this. Well, it's like kind of hard to tell, right? Like, it's not that surprising if he develops sepsis, not that surprising if he doesn't, given my prediction. Like, it's very difficult to figure out whether a single probabilistic forecast in isolation was any good or not. But like professional doctors don't just make single predictions, they have a whole track record. They might predict things about patients every single day. And once we have a track record, we can at least start like subjecting it to like sanity tests, sanity checks based on the data. Like we could say, okay, like, is there any statistical signature in this data that would be really unlikely if the forecasts were true probabilities? So for example, we can look at all of the patients for which the doctor predicted a 70% chance of developing sepsis. If these were real probabilities, about 70% of those patients would have developed sepsis, okay? So if that doesn't manifest itself in the data, that's a red flag. And we shouldn't just, audit the 70% probability. We should audit the 20% probability. We should look at all of the patients for whom the doctor forecast a 20% chance of developing sepsis and check that roughly 20% of them actually did. And if we do this for every value of the doctor's predictor and they pass, the doctor's calibrated. Those are the calibration tests. Okay, so, like you can do it in math, not just in pictures. So in general, we have some distribution over labeled examples. Okay, it's not important that they're binary, but let's, just for simplicity, think about binary labeled examples. So we've got just some joint distribution over like features and binary outcomes. And calibration just asks that the predictions we're making be statistically unbiased, not just overall, but conditional on the prediction value itself. So, if I look at the expected difference between my prediction f of x and the label y, right, that should be 0. Okay, if that were just 0 overall, that would be an unbiased predictor. And we're asking for this somewhat stronger guarantee that the predictor be unbiased, not just overall, but conditional on the value of the prediction itself. Amongst all of the patients for whom we predicted a 70% chance of developing sepsis, about 70% of them should. Now, there's all sorts of ways to measure calibration error. Like the first thing you need to understand is that I'm never going to have perfectly calibrated predictions, at least on the data. Like suppose I'm forecasting the probability that a coin comes up heads. Maybe it's a fair coin, I forecast correctly a 50% chance. But if I only flip it once, my bias is going to be 50% because, it'll either have come up heads 100% of the time or 0% of the time. So in order to have small bias conditional on the prediction, I need to have made that prediction many times, right? Like if I flip the coin 1,000 times, my bias will be small. If I flip it only once, it won't be. And so a classic way of measuring calibration error, the way we'll talk about it in this tutorial, is through what's called expected calibration error, which just looks at the conditional bias of the predictor, conditional on its own prediction, as averaged over all of the predictions it can make, weighted by the frequency of those predictions. So it's kind of like automatically doing this thing of penalizing the predictor less for bias on predictions it makes less frequently. Now, there's all sorts of disadvantages of this particular measure, and there's a whole literature that maybe I'll talk about right at the very end that tries to develop alternative measures that avoid some of these disadvantages. But this is the standard. This is the one we're going to talk about for the tutorial. And why should you care about calibration? We're going to talk about sort of strengthenings of this in a moment, but already just vanilla calibration already has a guarantee that maybe the first time you hear it seems a little bit miraculous. We'll also see that it's weaker than it seems at first blush. But the guarantee really is that it instills trust in predictions for every downstream decision maker. By which I mean, there might be a bunch of people who are consuming the predictions that you're making. They're trying to decide about what actions to take. Different decision makers might have different action sets. They might have different utility functions which map the outcome that you're trying to predict and the action they take to some number. The bigger, the better. And if your predictor is calibrated, the guarantee is going to be that amongst all of the ways they could map your prediction to a decision, like uniformly the best one is to just pretend that your predictions really are real probabilities and optimize accordingly. Okay, so here again, it is in math. It says, look, fix any downstream decision maker. A downstream decision maker is just defined by some utility function mapping actions and outcomes to a utility. If the forecaster that I have, call it F, has calibration error at most epsilon, then best responding to the predictions, by which I mean just choosing the action that would maximize your expected utility if only the outcome really was going to be one with the probability that I predicted, like in the world in which my forecasts really were real probabilities. Like, best responding to the forecasts is the best thing you could do in the sense that you'll have higher expected utility under the real distribution compared to any other policy you could have played mapping predictions to actions. Okay, that's the guarantee of calibration. One thing I want you to note, this is so simple, I'm even going to like force you to suffer through the proof on the next slide, but it's only like 4 lines. So like the one thing I want you to notice is that the decision maker is trying to maximize their expected utility. And so this utility, your expected utility when the forecast is p, that's a linear function of p, just because expectations are linear. Okay, and you know, the sort of gloss, if you want to remember this, it's just, you can't do better than to trust the predictions if they're calibrated. Okay, so why is this true? Well, like, let's sort of just write down what our utility is going to be for best responding to the predictions in the real world. When I say in the real world, what I mean is, well, if you look in here at the best response function, it's best responding to p, my forecasted predictions, but the utility is actually computed with respect to y, the real outcomes. Now, because the utility function is linear, this expectation over the label, I can take that inside the utility function because, well, the utility function is linear in the probability we're forecasting. But now, like, what I've got is expectation of the outcome given the prediction. But what calibration promises is that my forecaster is unbiased, conditional on the prediction. So the expectation of the outcome given the prediction is just the prediction itself. Now, if you look at this expression now, we're best responding to the forecast, and now the outcome actually is realized according to the forecast. In this world, in Optimistica, the prediction that I'm making is a real probability. Okay, that's what this algebra has done so far. And so, in Optimistica, in this world where the forecast I'm making is a real probability, of course it's a better idea to best respond to the forecast than to do anything else. That's what it means that it's a best response. This is the best action you could have taken in a world where these were real probabilities. And then just doing this algebra backwards, you can get back to the real world. Okay, so like seemingly magic, like the best thing you could possibly do in response to calibrated forecasts is to act as if they are real probabilities. Okay, that's kind of cool. Now, you might, at this point, think to yourself, okay, wait, that sounds like a little bit like too cool, like couldn't possibly be true. And this is the thought process you might like go through. So consider this sequence of patients for which the average frequency of sepsis is 40%. Like, there's not like a unique way to be calibrated. Here's one way to be calibrated. I could just make perfect predictions. I could say, okay, a patient who's not going to get sepsis, like I'll just predict a 0% chance of sepsis. A patient that is going to get sepsis, I'm going to predict a 100% chance of sepsis. You couldn't ask for better predictions than this. These are great. But like, I could also be a really lazy forecaster and not even look at the covariates of the patient at all, and just predict for everyone like the base rate, like a 40% chance of sepsis. And both of these are calibrated. Like, if you look at the first one, what does calibration ask for? Well, unbiasedness conditional on the predictions. On the days when I predicted a 0% chance of sepsis, none of them got sepsis. On the days when I predicted a 100% chance of sepsis, they all did. Perfect. I'm unbiased, conditional on the forecasts. But like this second terrible forecaster, he's also calibrated. Because I'm just asking for unbiasedness conditional on the predictions, and he never varied his predictions, so the conditioning event becomes very weak. If I look at all of the days for which he predicted a 40% chance of sepsis, well, that's all of them. And indeed, 40% of those patients got sepsis. So these are two ways to be calibrated. The first one is obviously very useful. The second one isn't useful at all. And so like, okay, like, how does that jive with the fact that I claimed that like calibration had this amazing decision theoretic property? Well, like the caveat is that in that simple theorem we proved, like the benchmark class was just policies that mapped the forecast to the outcome. And if the prediction is a constant, if I never predict anything other than 40%, that class of benchmark policies is just extremely weak. It corresponds to policies that also don't look at the covariates and only take a single action. Right, so like the guarantee only applies to decision makers who know nothing about the instance at all, other than the forecast we're making. If the decision maker has access to anything else, this guarantee, cool as it is, like no longer applies. And calibration also on its own like doesn't imply anything about accuracy, at least not better than the accuracy of the best constant predictor you could make, because as we saw, it's possible to be calibrated while predicting only with a sort of uninformative constant. And so, although calibration's kind of neat, like it's certainly not everything we want. Like it's a minimal desirable property, but we want more. Now here's a couple of languages you can use to ask for more. So the first is called multicalibration, which is just asking for calibration not just overall, but conditional on various functions of the context. Okay, so like if the doctor knows something about the patient other than the prediction, we're going to want our predictor to also know those things about the patient. And so to define multicalibration, just fix some collection of grouping functions that group the forecasts in various ways. These can be anything. So they can, for example, group patients by things that you think are diagnostically relevant, by their blood pressure or the gender of the patient or their age or anything else about their clinical history, for example. And then we'll define a bunch of distributions. There's, of course, the distribution over all of the patients, but then the conditional distribution conditional on these groupings. Like look at just the patients ages 50 to 55. Look at just the patients with high blood pressure. And multicalibration asks for a forecaster that is calibrated not just overall, but simultaneously on all of these conditional distributions. You want to be like calibrated for all of the subpopulations simultaneously, because the real probabilities, whatever those are, would be calibrated on every grouping. We know that this is feasible, but the hope is going to be that even for rich collections of groupings, that we can learn forecasts that satisfy this property efficiently. Okay, so like multi-calibration, as you start layering on additional calibration constraints, you're never going to rule out the perfect forecast. So there's always like something feasible in this set. But you're gonna start like ruling out the lazy forecasts. So for example, here's another sequence of patients. Now the overall frequency of sepsis is 50%, but suppose now that we can observe some feature about the patient, say their biological gender, and let's say that for female patients the prevalence of sepsis is 80%, and for male patients it's 20%. Okay, and say we want to be multi-calibrated with respect to this gender grouping. Well, we could still make perfect predictions. We could also predict 20% for male patients and 80% for female patients. Or we could try again this lazy predictor that just sort of predicts the base rate, 50% for everyone. Now, this first predictor is still, not only is it calibrated, it's multi-calibrated. Because not only is it unbiased overall, when I look at the male patients, well, on the male patients it predicts a 20% sepsis risk, and indeed 20% of them develop sepsis. On the female patients it predicts an 80% sepsis risk, and indeed 80% of them develop sepsis. But this lazy forecaster, which was calibrated as we saw, fails these multi-calibration tests because it overpredicts for male patients, it's biased upwards for male patients, and it's biased downwards for female patients. Okay, and so like multi-calibration lets you layer in these additional like calibration constraints. The groupings don't have to be disjoint, and as you layer in more and more, you only get sort of more and more accurate forecasters, and sort of in some sense, the game we're going to play in this tutorial is to try to choose the constraints that lead to the kind of guarantees we want for various downstream applications. Okay. Right, so these groups, how do you choose them? You choose them according to like what it is you want to do. Right, so they can be arbitrary and overlapping. Multicalibration kind of came out of a fairness in machine learning literature. So the initial motivation was that these would be like demographic groups. The probabilities should be meaningful for different demographic groups, maybe broken up by like biological gender or ethnicity or age. But they could be, for example, like the level sets of benchmark policies. That's what we're going to choose them to be in Natalie's part of the talk, where we try to give decision theoretic guarantees downstream. Or they could be some functions of history of interaction with the person you're talking to. Okay, maybe that'll give us, good properties of the interaction. That's the groupings we're going to choose in Ira's part of the tutorial. Okay, and just because like we're all gluttons for punishment, let me define one further abstraction before I finally like tell you an algorithm for obtaining this. Okay, so like we're going to ask for predictors that pass lots of statistical tests. And there's no reason those statistical tests have to be calibration tests. Okay, so more generally, let's say we have an arbitrary collection of tests where each test is just some weighting function that maps features and predictions to like a weight that can be between -1 and 1. Then we'll say that a predictor is outcome indistinguishable with respect to these tests if in the worst case, or if for all of the tests, if I look at in expectation, like the correlation, the product between the value of the test, given the example in my prediction, and like the residual of the predictor, the difference between my prediction and the outcome, that this should be 0, or at most epsilon, if we ask for epsilon outcome indistinguishability. Okay, and so this is like asking that, in a world in which my forecasts are perfect, in a world in which like the probability that y is 1, given my forecasts and given the covariates, actually is what I'm predicting, like I'm predicting real probabilities. Like that world should look just like the real world to someone who can only see the correlation between the tests and the outcome. Okay? And the form of all of the arguments we're going to go through are going to be to sort of observe that things work out really well in the world in which my forecasts are perfect, of course, and that the application that we have only requires looking at the tests, only requires looking at the world through our carefully chosen set of statistics. Okay, so here we are. We've got the real world, we've got Optimistica. In Optimistica, the features are distributed just as in the real world. What's different is that the labels are generated according to like a Bernoulli random variable governed by our predictions. Our predictions are perfect in Optimistica. And outcome indistinguishability promises that anyone who can only look at the correlation between these tests and the outcomes can't tell which of these two worlds we're in. That's the guarantee we're going to leverage. Okay. Finally, like a collection of tests. I've basically been giving you definitions so far, right? Like, here's what it means for some predictor to be outcome indistinguishable with respect to the real world. Well, in the second parts of the tutorial, we're going to see how to use this guarantee if you have it in various ways. But it wouldn't be interesting unless we had good algorithms for obtaining it. So what I want to do in sort of the last, say, 10 minutes of my part of the tutorial is to show you like a cool argument that such predictors exist and actually like that they're not hard to find even in surprisingly challenging settings. So I'm going to show you that we can, given any set of outcome indistinguishability tests, find a predictor that satisfies all of them, not just in the easy setting where there's a distribution and examples are drawn IID from that distribution, but in this much harder like sequential adversarial prediction setting. And that despite the fact that we're going to be operating in this much more difficult setting, you can still satisfy all of these properties at kind of like the statistically optimal rate. Meaning if you want epsilon outcome indistinguishability, the number of samples you need is only going to scale with the log of the number of tests over epsilon squared. So you can feel free to ask for this property with respect to tons of tests, not all of them. If you ask for like all possible tests, you'll get back to this impossible problem of individual probabilities, but you can ask for exponentially many. Okay, so what is this like difficult sequential adversarial setting? So it's like a prediction game that's going to take place in rounds. And at every round, the learner observes the features that are relevant to the prediction that day, and then they have to make a prediction, a number between 0 and 1. And only then does the learner observe the outcome. And like the key thing about this setting is there's no distribution. Like we can imagine that this sequence of features and labels is chosen by an arbitrary process, even an adversary whose only goal is to screw up whatever guarantees you're trying to prove about your algorithm. And we can then, after the fact, evaluate whether our predictions were outcome indistinguishable. Well, what does that mean? Outcome indistinguishability was some expectation over a distribution. There's no distribution here. Well, like after the fact, there's like an empirical distribution. There was actually a sequence of predictions and features and realized outcomes. And we can just ask that you look outcome indistinguishable after the fact, no matter what happened. Okay, you have to be able to do this for every possible adversary. By the way, like, we don't necessarily believe that in every setting there is an adversary, although sometimes there might be. But if you can give an algorithm that works in this difficult setting, then it handles arbitrary, like, unexpected distribution shift, for example. Like if you don't need to make any assumptions at all, then you don't need to worry that your algorithm fails because your assumptions aren't satisfied. Okay. And I sort of said this was like, you should think about this as a prediction game. Like it really is, like, the right way to think about this is to think about a game. So let me remind you about zero-sum games. You know what a zero-sum game is if you've ever played rock, paper, scissors. So in a zero-sum game, there's a minimization player. There's someone who's trying to make some number small. We're going to identify that with the learner. There's a maximization player. There's someone who's trying to make the same number big. We're going to identify that player with the adversary. And then there's a utility function, the thing that the minimization player is trying to minimize and the maximization player is trying to maximize. And this just maps a choice of actions for the two players to a number. And it's important in rock, paper, scissors that you're allowed to randomize. Like I should be able to not just play rock all the time, but randomize between rock and paper and scissors. So we'll let the players in these games randomize, and the players just care about their expected utility. And the key thing about zero-sum games, like the one thing you should know about zero-sum games, and this is von Neumann's minimax theorem, is that the order of play does not matter. Like, if you have to go first and announce your strategy to the adversary, like I say, guess what? I'm going to randomize uniformly between rock and paper and scissors. That does not put you at a disadvantage. You can do just as well if you have to announce your randomized strategy to the adversary and let them best respond as you could in the seemingly much easier setting in which they announce their strategy first to you. That's like the one fact you need to know about zero-sum games. And so, first let me give you like a really slick, non-constructive argument for why it should be possible to learn predictors that are multi-calibrated, that are outcome indistinguishable, even against adversarial sequences. Like, sequential learning is a zero-sum game played against an adversary. What you need to do is you need to commit to an algorithm, like write it down in pseudocode in your ICML paper, and then you need to assert that this algorithm will do well for all possible adversaries it could face. So by publishing your ICML paper, you're committing to your strategy, and you're asserting that an adversary who's allowed to read your ICML paper still can't screw up the guarantees of the algorithm. Okay, this is like the difficult setting of online adversarial learning. But it's like a zero-sum game. Like I would like to minimize at the end of time my calibration error, my outcome indistinguishability error. The adversary would like to maximize it. Well, by the minimax theorem, this value, the value of the game, how well I can do by playing the optimal algorithm, is exactly the same as how well I could do in the seemingly much easier setting in which the adversary had to go first and tell me what their strategy was. If they tell me what their strategy was, that's like telling me just before I need to make my prediction what the distribution on outcomes is. They have to say, hey, this patient has a 20% chance of getting sepsis. Now, obviously, in that case, I can be super well calibrated or outcome indistinguishable because now I can just predict the real probabilities. I'm like, all right, guy, I predict a 20% chance of sepsis, and guess what? I'm right. So in this seemingly much easier setting, of course I can satisfy multicalibration or outcome indistinguishability tests at the optimal rate. Like, the adversary is just telling me the true probability every day, and I can just repeat it back. And the magic of the minimax theorem is that I must be able to do just as well in the seemingly much more difficult setting in which I gotta write down the algorithm first. Now, just amazing. But this is a non-constructive argument. It doesn't tell you what the algorithm is. In principle, you could solve a zero-sum game, but the zero-sum game is enormous because the strategy space here is the set of all possible algorithms. So truly a non-constructive argument. But we told you at the beginning that these algorithms were gonna be efficient. And in fact, although this non-constructive argument was you might worry that there is no efficient algorithm for doing this, some kind of minimax magic. There is actually an extremely efficient algorithm, and if you bear with me for 5 minutes, I'll even tell you what it is. Okay, so outcome indistinguishability asks that after we're done interacting with this adversary, we satisfy a collection of linear constraints that on average over the transcript, the degree to which we violate each of these constraints should be 0. And so that's like saying the time average of these test statistics should approach a polytope. Each of these linear constraints defines, a half plane, and the polytope is the intersection of all of them. And so that makes this a Blackwell approachability problem, if you've ever heard of Blackwell approachability. If you haven't, look it up, it's pretty cool. And also, if you haven't, don't worry about it, because I'm about to tell you how to do it. It's surprisingly easy. So suppose, your biggest enemy, there's some hater who's just betting against you. It's gonna take pleasure every time you fail. And what they're doing is they are gonna maintain a distribution over bets against you. They're gonna do it with what's called a no regret algorithm. And if on some round they bet that you're gonna fail to satisfy test A, their joy is gonna be directly proportional to how badly you screw up test A. You're supposed to make the product of the test A with the residual y minus p less than or equal to 0. If you don't, if that's positive, they're gonna experience positive joy. And they're hedging. They're not betting only on one test. They're sort of dividing their bets against you as a distribution across all of the tests. And so at round T, the joy that your hater will experience is the expected degree to which you violate the constraint that they bet on in expectation over their distribution of constraints. Let's call that your hater's joy at round T. Now, since they're running a no regret algorithm, they're going to be promised near optimal joy. This is a great way to bet. So let's say that at the end of time, your biggest failure is the worst case over all of the tests of how much you ended up violating that test. And the no regret guarantee promises your hater that their joy at the end, on average, is going to be at least as big as your biggest failure, minus this regret term, this thing that'll go to 0 the longer and longer you play this game. Okay, so your hater is going to do really well if your biggest failure is significant. And so the key to the algorithmic strategy, the main idea, is to play so as to minimize your hater's joy. So, let's say that here's the distribution over predictions you should play every day. You should play the distribution over predictions that minimizes, in the worst case, over what the label might be, your hater's joy, how happy they are. Now, remember, your hater's joy is kind of linear in the outcomes. It's just like the expected value of this residual as weighted by these test functions that they're betting over. Now, of course, if you knew what the label was, or at least if you knew what the expectation of the label was, you could just always predict that expectation, and it would zero out your haters' joy no matter what they were betting on. Okay, now you don't, but what you're doing is you're playing the strategy in the zero-sum game that is optimal. And remember, in zero-sum games, it doesn't matter who goes first. Okay, so by playing this strategy, you can actually guarantee that your haters' joy is zero in expectation. Now you're solving a zero-sum game here, but now it's a little zero-sum game. The strategy space is just, here, like there's just two constraints. It's like the label could be 1 or it could be 0. So we're still solving a zero-sum game, but now it's now it's like a 2-constraint linear program. Now it's really easy. And so you play every day so that your expected hater's joy is 0. But your hater was playing this great strategy. They were playing a no-regret algorithm. So their expected joy is greater than your biggest failure minus this regret term. How can that be? Well, the only way it can be is that if your biggest failure wasn't that big. If, in particular, your outcome indistinguishability error is less than the regret term, root log the number of tests over t. Okay, and it's the algorithm. It's pretty simple. Like you just instantiate something like multiplicative weights. Every round you solve a 2-constraint linear program, you're good to go. And this is solving some problem in this difficult online adversarial setting. There's no distribution here. But if there is a distribution, like if you just want to train in the standard way, you've got a bunch of labeled examples drawn from a distribution, you'd like to do well on the distribution. Well, since this is solving only a harder problem, you can actually use this to solve the standard batch learning problem as well. Just feed it examples from the distribution, and you're good to go. Okay. Finally, just to close the loop, what does this outcome indistinguishability thing have to do with multicalibration? Well, suppose we're making predictions on some grid. Okay, I'm not predicting arbitrary real values. I'm predicting 1% chance of rain, 2% chance of rain, 3% chance of rain. Expected calibration error, the way we defined it, sums up over all of the different prediction values of the frequency with which I make that prediction value, of the magnitude of the bias that I have having made that prediction value. There's all these absolute values. But the absolute value of a number a is just a times the sine of a. And so another way to write expected calibration error is just the maximum over all of the different ways of assigning signs to my different prediction values of the sine-weighted residual, okay, times the group. These are just outcome indistinguishability tests. So, outcome indistinguishability. So multi-calibration is just a special case of outcome indistinguishability. Now, the problem here is that multi-calibration asks for lots of tests. We know how to get outcome indistinguishability, and we pay for log of the number of tests, which isn't too bad. But if there's a lot of tests, we start to feel it. And so, unfortunately, multi-calibration starts to require more samples than you might want to pay. 1 over epsilon cubed in 1 dimension and 1 over epsilon to the k in k dimensions. This can get expensive. But really, the problem is just that there's too many tests. And so for downstream applications, you often want to ask for only those tests you need. So let me hand it off to Natalie.
Cool. Hi, everyone. I'm Natalie, so I'm going to continue from here. So now we understand that there is an algorithm that you can use in order to get these great guarantees. But even if you didn't understand it, that's okay, because the stuff I'm going to talk about now just requires believing it exists. It doesn't require understanding the way it works. So worry not if you were confused. Okay, so what I'm going to talk about now is I'm going to talk about what happens when we take these ideas and we bring them into more complicated settings. So when we actually care about the decisions we're making, and then also how we should deal with the fact that in addition to wanting these guarantees, we live in a world that has very good, very complex models that might not have these robust guarantees, but nonetheless, which might have some general good accuracy that we want to take advantage of and not lose when we attain these robust guarantees. So we're going to start with this action thing. And so first, let me complicate this running example. So we've been talking about sepsis, and of course, none of us here are doctors, but just to give a sense of the sorts of applications one might use it for. So apologies to any medical professionals in the audience. But we've been talking about, okay, the outcome is just one of two things. So either the patient has sepsis or doesn't have sepsis. But more realistically, if you're a patient and a doctor cares about figuring out your outcomes, the state that you're trying to predict could be far more complex and more high dimensional than just will they develop sepsis or will they not develop sepsis. So it might include their vitals, some entire future clinical trajectory of all their vital signs, all their blood tests over the next 24 hours. And this is a very high dimensional object. So, we've just talked about how, it's great. We can get these calibration guarantees. These can give us really good downstream guarantees on what to do, as long as we can just be unbiased with respect to some things, as long as we can pass these tests. And there's not that many tests. But that's true as long as the thing we're trying to predict is low dimensional. But if you start looking at high dimensional predictions, as we all frequently are, we do actually run into a problem, which if it's really high dimensional, you might have to pass a lot of tests. So we would like a better way than to just necessarily try to be completely calibrated to this very high dimensional object we're trying to predict. So one thing that will often be useful is to think about, going back to this idea of we're not trying to really get probabilities. What we care about is deciding what did we need to be true about these probabilities, and how can we figure out the sufficient statistic that we need in order to get that same thing, even if we're not predicting true probabilities, because it's not even clear if that's possible. What do we need? And so sometimes what you need is that what you're trying to do is make good downstream decisions with those predictions. So even if your prediction is very complex, right, that the entire future health trajectory of this patient, you might care about this because you're trying to make medical decisions for their treatment, right? And this might not be as high dimensional of a space, right? There might be some particular treatment actions that you could take. And what you care about isn't that you figured out exactly what their heart rate would be at hour 6. You cared that you made the right treatment decision. So we can imagine, for example, here, there are, 4 different, exemplary actions that the doctor could take. And so if our main goal is good downstream decisions, can we use less tests and therefore take this algorithm we talked about and make it efficient again? So the answer is yes, and that's what we're going to talk about now. So we're on to the second section, good decision making. Okay, so before we dive into how you do it, I want to talk about what I mean by good decision making. What makes a decision good? So we can imagine that we have some doctor and they have some utility function that maps from some state, that's a thing that they're trying to predict, and some action. That's the thing that they're going to do, the intervention they're going to take. And so you can imagine, of course, in many settings, including this one, they should care not just about what the state was, but also how it combines with the action they took. So if it turned out that it was a patient who had a broken arm and the action the doctor took was prescribe antibiotics, well, I'm no medical professional, but I think, that's not what happens to me when I have a broken arm. They give me a cast or something. Meanwhile, if they really had sepsis, then it might have made a lot of sense for them to prescribe antibiotics, right? So you have this interaction between the state and the action, which should determine how happy the patient and therefore the doctor is with the health outcome. Okay, so just a little notation for bookkeeping going forward. We're going to talk about, given this prediction, there's some prediction f of x that you're making based on the features about what the actual state of the patient is. In this case, maybe, what their true, complex, high-dimensional diagnosis is. Then d of f of x is what is the decision that you would make based on information that is the best thing for them, assuming that your prediction about their state is correct. Okay, so it's a mapping of a prediction to an action. And our goal here is going to be to ensure that the decision maker when making this prediction, when doing the best they can according to the predictions of our prediction algorithm, have no swap regret. Now, what is swap regret? Swap regret is great, and I'm going to tell you about it now. So, in essence, swap regret measures how well a decision maker can improve in some metric, your favorite proper, loss, so let's say squared error right now, by swapping all the times they played one action with a different action. So we can look at this example here. I kind of want, hello, good, okay, cool, now I can turn my head. It measures how much a decision maker can improve. So let's look at an example. So you might have many different types of patients that have different ailments and different treatments. And it would, in order to have no swap regret, here's what would need to be the case. The doctor would have to look back at all the times. Here we can look at, okay, these different subsections based on what action was taken. All the times they prescribed antibiotics. It should be the case that in average over all of these instances, this was the best action to take. So it was better than doing surgery in all these patients. It was better than giving a cast to all these patients. Now, we're not promising that it's better than picking a different thing for each of these patients, right? That would be getting back to optimizing for individuals, predicting individual probabilities. We're not hoping for that. We're just saying that, okay, overall, on the times you took this action, it was the best action. And you would also want this not just on the times that you did antibiotics, but also all the times you prescribed a cast, this was the best thing to do. And also on all the times that you did surgery, right? So for all of the actions that you could have taken, this was actually the best action on average. Okay, so if that's what we care about, if our goal is that the predictions that are being made are in fact, at least when we think about the best responses that they induce, we actually end up with them being trustworthy according to the actions. Okay, how should we think about that in this framework of outcome indistinguishability? So going back to this framework here of real world and optimistica, what we care about here, as a general statement, we're looking for things of the form, they're indistinguishable to some statistic, which has some function A, multiplied by the state of the world y, which is like in one of the worlds, it's the true state. In the other world, in Optimistica, it's the actual thing our predictor is making magically. So what are we looking at here? So again, think about this decision rule d of f of x. What we want is this particular property down here. So let's break this down. So what I'm saying is, on the subset of days that the decision rule operating over our prediction leads to particular action A, we should be unbiased. So this is a weaker condition than full calibration. We're not asking to be fully calibrated on the state. We're just saying that, okay, instead of looking at like all the particular levels, that's my prediction, let's look at all of the times my prediction says that the thing that you should do is take this action. Well, if we bunch all of those together, then you look unbiased on that particular set of data. So, right, we don't need to be fully calibrated, just unbiased on the best response regions. Okay, so why is this enough? Okay, so imagine that you are a doctor, and there is a predictor that you're using, which is recommending, is giving you some prediction on the patient state. And based on that, you see that the action that would be the best, if this really was the right state, is to prescribe antibiotics. So you then would ask yourself, does this mean I should, in fact, increase antibiotics? Okay, so certainly if the world we were in was Optimistica, the answer would be yes, because that's a world where our predictor is really, really good. Cool. Okay, well, what else do we know? We know that in aggregate, over the instances where, in fact, our predictor suggested the best thing was antibiotics, we can't distinguish between Optimistica and the real world. So, from all that we know, in our model of the world, in fact, the expected utility of antibiotics looks the same in both settings. But the expected utility of every other action also looks the same in both settings. So if antibiotics was the best before in Optimistica, it's still the best. Okay, so that's really the key to decision calibration, is we don't actually care anymore about full calibration on the whole state, because what we care about in the end isn't accuracy in any way. Like, we're no longer necessarily saying, oh, look at this prediction, we're promising that it reflects, even any sort of, calibration properties. We're just saying it's gonna be good for the decisions you wanna make with it. And so we need less to be guaranteed to do that. That's a weaker condition. And so now we have these tests, we have less tests, and at this point, we can just apply that algorithm that Aaron talked about, which you either understand or you don't, but it exists. And we can sort of directly plug in these particular tests. And how many are there? Well, there's just one for every single action. Okay, so that's decision calibration. So now we're going to move on to the second part of this section, which is this idea that Aaron mentioned at the beginning about how this is a lightweight framework that can be placed on top of some very complicated, maybe your favorite expensive model that you worked very hard to train. So, you might say, I already have such a great model. It gets pretty good accuracy. Like, sure, I don't know how to prove robust guarantees on it in the face of distribution shift, but it works pretty well. It uses lots of complicated techniques. Like, I don't want to just throw it away just to use this stuff that you're talking about. And the great thing is you don't have to. And so I'm going to tell you how. And I'm going to tell you one way to do it, which I think is maybe kind of intuitive and straightforward, and also will lend itself good to intuition that will come up later in Ira's section. And then I will tell you another way to do it, which, if all you really care about is getting the guarantees of your model, is probably the right way to do it in this setting. So, okay. Back to this. We're now talking about this does no harm section here. So, does no harm, even if you already had a really great model, don't worry, we can get all the guarantees from that model and from these things we're talking about here. So, warm up first. So here's something that you could do. So imagine you have a model, you love it, it's this little guy here. What it does is it takes in patient data and it outputs some % probability that they'll develop sepsis. So for a moment, we're gonna move back to the setting where you're actually making quite simple predictions. We'll go back to this high dimensional in a second. Okay, so what we're gonna do is we're just gonna come up with a post hoc calibration method that's gonna map just the outputs of this model to maybe some slightly tweaked probabilities. So note here, we're not reaching into the complicated algorithm at all. You don't need to open up the black box of some arbitrarily complex model that you're using. And you actually don't even have to open the black box of the algorithm Aaron was talking about before. Like, you have some great model. We have a way of taking things and making calibrated predictions. Let's put them together. Okay, so here's how we're gonna do it. So you have your model, and it makes lots of predictions. It could be really good, it could be really bad. We wanna make sure we do at least as well as it, though. And maybe it's doing some stuff that we aren't able to do, right? Because remember that, calibration in the end, all it's really guaranteeing is that, you're at least being unbiased, right? One thing it could have been doing is just throwing away all contextual information and somehow figuring out the average and predicting that. So maybe your model, even if it is biased, is still like getting lower squared error because it's doing better than that. It's doing some more interesting stuff on some of the subsections of the data. So okay, so like your model does something, and for all of these patients that it's seeing, it's coming up with some probabilistic predictions of the % chance that sepsis is seen in the next 24 hours. And we can imagine, these color bars here are separating the different level sets of your predictor. So, okay, here's all the times that the prediction is near 70%, here's all the times it's near 20%, etc. Okay, so here's something we could do. We could, take some subsets of the data, say okay, let me look at all the times it's between 70% and 80%, call those kind of close enough to each other. And I'm gonna feed all of those instances into one calibration algorithm. And I'll do the same thing with all the ones that are near 20%, and so on, for all the different level sets I'm going to define. Okay, and then I'm going to run calibration, my calibration algorithm on the subsets that were picked by the cleverness of your algorithm. And then the outputs that I'm gonna come up with are the ones from the calibration algorithm. Okay, so the claim is that this is good. So if we do this, we're going to end up with something calibrated, and that squared error is going to be only lower than the prediction that was being made by your favorite complex prediction algorithm. So why is that true? Okay, so when we want to predict the squared error of some predictor, we can do it by separately looking at all the level sets of your predictor. So let's look at the squared error on all the times that your predictor predicted near 70%, near 80%, near 90%, right? So we'll look at 70% as an example. So on all the times when your favorite predictor predicted 70%, the best possible case scenario for squared error here is that really it was true that about 70% of the time, the patients develop sepsis. So why is this true? Well, it's because squared error is a proper scoring rule, which means that if you want to minimize it, then the best case scenario is that you are actually unbiased. This is also true for other great things like log loss. So lots of great proper scoring rules out there. Proper scoring rules are super fun. Okay, to be clear, this could be worse. So what we're showing is that we're definitely, only decreasing squared error. So I'm trying to be very optimistic about what your previous favorite predictor was doing. It could be biased here. But the best case scenario, because we're literally looking at a level set where it's predicting the same thing all the time, is that the thing it's predicting is exactly the average. Okay. Ooh. Sorry. Okay. So meanwhile, what's going on after we do this post hoc calibration on it? Well, what's happening is we're going to take this whole section on which your favorite model predicted the same thing all the time, and we're going to end up with some set of calibrated predictions. And those could include, it could be that it also predicts the same thing all the time. It could predict different things. But the worst case scenario here is that you actually predict the same thing every time. Because at the very least, calibration guarantees unbiasedness, right? Kind of the worst way you can be calibrated is if you don't pick up on any kind of context clues and you're just predicting the mean the whole time. But if you do that here, that's the worst case scenario for your squared error. And you're actually still doing at least as well as the other predictor because you're taking advantage of the level sets that it already defined. So when we fine tune on the predictions by just adding in calibration, this is only going to help. Okay, and now when we move on to a more complex prediction, which could be your entire couple hours of patient data, you might worry, okay, what does it mean to look at the level sets here, right? Do I have to look at a different level set for each dimension of my data? So again, we can think about the actions. We can say, okay, instead of splitting up by all the different level sets of my predictions, I can say, well, let me run a different calibration algorithm for all the times the predictions from your favorite algorithm led to looks like the best thing to do is no intervention or surgery or antibiotics or something else. And the same general idea now applies. The best case scenario for your algorithm is that was the right thing to do on average. And in my algorithm, I'm definitely getting that guarantee, but it also could be that I'm able to split up that data even further and get more fine-grained guarantees. Okay, and so what's the guarantee you end up getting out of this? Well, you learn that on average, over the times you take a given action, it was in fact the most effective action. And the medical interventions that you're making are at least as effective as those proposed by your favorite model. Okay, so that's great, and that I think, keep in mind the intuition that you can take some previous information given by some maybe very complex and very good and complicated algorithm and iterate on them by adding calibration to make them better, because that's going to come into play in Ira's section pretty soon. But I want to also show the power of this outcome indistinguishability framework by showing how when you want to move on to, for example, multiple predictors and stay in this high-level setting, there's actually an even better way to do this. So what do we really care about? So we can see maybe a problem if what we try to do now is say, okay, I want to compete with multiple predictors. One thing I could do is I could do the same trick and take intersections of all the different level sets of the predictions, but this seems tough because now we're scaling exponentially with the number of predictors. The number of intersections of the prediction sets could scale exponentially, and so that seems like a bit of a problem. So can we come up with something better to do? Okay, well, let's go back to this outcome indistinguishability framework. Okay, so actually, here's the goal that ends up being right. So what we really care about here is that the difference in, if we pick one of these particular models that we want to compete with, and we can do this for all of them and add up all these tests, what we care about is that the difference between my squared error as the new predictor, f of x, and the squared error of this model is the same in both worlds. Right? So why is that good enough? Well, we know, again, going back to this great trick about Optimistica, things are just great in Optimistica. In Optimistica, we're doing so well. So in Optimistica, f of x, this predictor that we're generating, really is the best thing, and so there's no other predictor out there that can outcompete with it in terms of squared error. So the best case scenario, or I guess the worst case scenario for us, is that there's something else that's just as good, but nothing's better. So if I can say that in the real world, the gap between my squared error and the squared error of the competing model looks like it does in Optimistica, well, that means that my model is outcompeting those other models in the real world as well. So, and maybe just to see, right, we're not actually saying that the total error is the same, just that the gaps between them are the same. So here in Optimistica, f of x, I should have inverted this. So you can see here what I've shown is that f of x is the biggest one. So that would make sense for utility. But if we're looking at squared error, I really should have shown that to be the shortest one, right? So if it was shorter over here, it would also be the shortest one over there, and that would be great because it means it's the best out of all the squared loss that we're looking at. Okay, and it turns out that if you just take this expression here, and you write it out in the, you do a little bit of multiplying squares together and canceling stuff out, then the right form to write it in to look at outcome indistinguishability is that the statistic you want to be indistinguishable with respect to is the prediction of the model minus the prediction, or I guess of the competition model, your favorite model, minus the prediction of the current predictor that you're building, times the state of the world. So we need it to be that this looks the same whether or not the state of the world is y, the real state, or whether it's this, magical y bar, which actually looks exactly like our predictor, the one that's drawn in Optimistica. Okay, so what's really nice about doing it this way is we just need one test for each predictor here. So remember earlier, we were, if we wanted to compete with one particular model, what we were doing is we were coming up with a different test for each of the level sets. Now, for a particular model, you just need one test. And if you now want to add on multiple different models and compete with all of them simultaneously, we don't need to worry about intersections of level sets. We just need one test for each of those models. So this is a really nice way, once you think about, okay, what is the thing I need to be indistinguishable, this ends up being a really nice way to elucidate the most efficient way to add lots of nice stuff to your calibration guarantees. Okay, so one more note here for this section. So this post hoc argument was pretty lossy that I made before. We're actually doing a little better than what I was saying, right? So I was saying, okay, best case scenario, worst case scenario. There's formal ways in which the described procedure is even better than just do no harm. In particular, what's happening when you take the level sets of the predictor and then add calibration on top is that if those level sets did have calibration error, if they were biased, you're going to eliminate that bias by making sure your final predictions are calibrated. So really what you get is that the squared error of your final predictor isn't just weakly better than the predictor before, but it's actually going to improve by the calibration error of your favorite predictor. And And this notion has a formal name in the literature. It's called calibrating. And so, if you're interested in that, this is like a nice thing to look up. And yeah, so that is the end of that section. And now I'm going to bring up Ira to finish us off.
All right. I hope everyone's feeling awake, alive, and enthusiastic still. I know it's been a bit. I wanted to say, for the folks who are kind of standing against the wall in the back, there's actually a lot of seats over here if you want to mosey over. You can go for it, yeah. Knock yourself out. All right. So, Aaron told you how to interpret probabilities. Now you know how to do that. And even better, Natalie told you how to make good decisions. So you're like almost, set for life. But here's the thing you don't know how to do yet. What you don't know how to do is how to collaborate with others. So that's what I'm going to tell you in this part of the talk. All right. So increasingly, in real life, we are interacting with machine learning in what you might call collaborative settings. So what I mean by this, in this sort of toy medical example that we've been using, it's not the case that a patient is going to the hospital, their information is getting fed into a machine learning model, the model spits out a decision and best response action for that particular patient, and then they are treated and sent along their way accordingly. What at least I hope is going to happen with the use of machine learning models is that there's also a human doctor in the room, and she also sees the patient, and she's asking what to do with the patient, and she might use the output of the model as part of her decision-making process, but that's not the only thing she's using, because she's a doctor who has, years of experience, and she can see the patient in front of her. So hopefully, at least, she can use the model's predictions along with her own intuition and knowledge to make that choice. Right, so that's what I mean by it's a collaborative setting. Now, the thing I'm going to talk about in the rest of this talk is how can we think about getting principled guarantees in these kinds of interactive settings. So either where you've got like a model interacting with a human who is making a decision or making predictions, or you could also imagine these in sort of distributed other forms of settings where you maybe have like two different machine learning models or agents interacting. All right, so how should we think about these settings? Well, the first thing that's kind of useful to notice is that this type of interaction or collaboration is most interesting in contexts where the patient or the person who you're making a prediction about, where their features are distributed across the two agents. So it could be true that the patient is walking into that room and they've got some like lab test results or something, and like both the doctor and the ML model have access to those lab reports. But also there's some features that maybe only the machine learning model has access to, right? Like maybe that patient has 10,000 pages of their complex medical reports over the last 5 years, and like as a human, I'm not super good at absorbing all of that information. I can read a lot of it, but maybe that's like a little bit too much for me to read. And similarly, there's also information that human doctor has that the model doesn't, right? Like the doctor's in the room with the patient. They can tell, are they making eye contact with me? Like what is their vibe? I don't really know how to like communicate vibe to a ML model. That's just me personally. So they've got all these things that they can't necessarily communicate to the model, right? And then they're making a decision in this combined setting. And throughout the talk, we're going to talk about this as if we have some feature space, x sub m, that the model has access to, and x sub h that the human has access to. And they could be overlapping, but they could also have sections that are disjoint. And we're going to think about that in particular. Okay. So, in a perfect world, what could you do? If you can actually write down all of these features, you could say, well, we could just have them exchange those features to each other, and then they could make a decision based on that sort of shared full feature set. Now, why can't we do that? Well, like I said, we don't really think that we can actually articulate necessarily what all those features are in the first place. And secondly, communicating that could be really hard, right? So if a machine learning model has a gigantic feature representation of that patient, they could maybe you could hand that as a report to a human doctor, but she's gonna be like, I don't know how to deal with that, right? And similarly, I don't know how to describe vibe. to an ML model. So we can't really do that. And like, heck, even if we could, in a sense, this is kind of a setting where we have two incompatible models, right? Where it's like the information is unreadable by the other person's like decision-making process. And moreover, it would be some super high dimensional information. So this is like too expensive from a communication complexity point of view. Okay, so what could we do instead? Well, one thing we could do is you might say, well, hey, Ira, like the features could be super high communication, but like if we're making a prediction or making an action, like that is something that I can articulate. Like I could say, well, I predict that this patient has like a 10% risk of developing sepsis in the next 12 hours, and the model could do the same thing. And then like maybe we could just take those two predictions and there could be some sort of aggregation rule for them, right? We could take their average or majority vote, or we could say for this subset of the patients we should always follow the doctor, and this one we should always follow the machine learning model's predictions. But this, it turns out, is too weak of a guarantee to give, or too weak of a setting to give good guarantees. So there's a variety of different results in this space, but it's essentially like all of them have this no free lunch kind of flavor. So what I mean by that is that for any aggregation rule that you pick that just ingests the predictions of either party, you can always construct kind of like a bad distribution or a hard example where doing this aggregation process and then spitting out the resulting prediction is going to be like worse for one of the two agents than if they hadn't even collaborated in the first place. And that's no good, because we really only want to be using these like ML systems in practice if you can guarantee the doctor like, hey, this is going to actually help you. At least on average, it's going to help you. So, is there no hope? Am I done now? Well, no, we're going to get around this. Huzzah. And the way we're going to get around this is we're going to allow for interaction between the model and the human. So they're still going to be making predictions, but they're going to be predicting and then telling the other person, and then she's going to be able to like update based on what she just heard, and they're going to iterate. We're going to iterate for not too many rounds, so it's still going to be way less communication required than it would be if we were sharing the features. It's going to be tractable. But by doing this, we're going to get around this sort of impossibility. All right. So the doctor could say, you know, I think the prediction of sepsis is 10%, and then maybe the model actually thinks it's like way higher. Maybe the model thinks it's 95%. And now the doctor could say like, ooh, okay, well, I thought it was 10%, but hearing you say that it's 95% makes me like adjust my belief a little bit. So actually maybe I think it's 35%. And now the model can do the same thing and say like, okay, well, I know that you know information that I don't know. So I'm going to update my belief, and I'm going to update it to 68%. And maybe at this point, the doctor said, okay, how about 65%? And at some point, they could agree. Hopefully in few rounds of communication. So that's the setting that we're going to be talking about for the rest of this part of the talk. All right, so as a disclaimer, I'm going to talk about all of this as if we are making predictions in between 0 and 1. So these are going to be real values that you can think of as representing probabilities. And oftentimes we'll think about them like discretized to some grid of like, you know, you can only predict 0, 5%, 10%, 15%, and so on. You can also think about these as like sort of approximate buckets, and our guarantees will scale accordingly. Okay. But if you prefer, you can also think about these results in this sort of, where you're making a decision that's a best response to the prediction, so you've got some sort of action space, like what Natalie was talking about earlier, and more or less all of these results generalize. But for the purposes of this, I'm going to just talk about it as if we were making predictions. Okay. So, why might this help? Well, one thing, it turns out, that people for a while have been talking about at least agreement and showing that you can reach agreement after relatively few rounds of communication. So in 1976, Oman showed that if you have two Bayesian rational agents, then they cannot agree to disagree as long as they have some kind of shared prior. So what does this look like? This would be a world where we're all Bayesians, and the patient comes in, and we have some sort of prior distribution about the patient's conditional label expectation. And that is shared between the model and the human. And again, these Bayesian agents, because they're rational, are gonna sort of like update their belief based on what the other agent says. So, maybe the model thinks the risk is 90% given the secret bits that they have access to, but the human doctor could be like, well, okay, I thought that the risk was 10%, but I know that you think the risk was 90%, so I'm gonna update my posterior accordingly. And then the model can do the same thing, because the model can be like, well, I know what I know, and I know what you know that I know, and so on. And they keep updating their posteriors until they agree. And Oman showed this was possible. Okay, cool. So we have agreement. Great. Are we done? Again, no. Well, first of all, don't know if they've agreed to anything good, right? So we'll have to work with that on that part later. But moreover, we don't even know that they're going to agree in a finite reasonable number of rounds of communication. So that's a bit of a problem. Okay, well, it was a problem until 2004 when Scott Aronson showed in a great little paper that as long as the underlying state space is finite, you can reach approximate agreement with high probability in a polynomial number of rounds. And he showed that you can do this even by only communicating one bit of information every round. So that's pretty cool. So now we've got tractability, right? We know that you're gonna reach at least epsilon close to agreement, meaning that maybe I could think that the patient's risk is 65% and the other person could think it's 64%, and that's within 1% of each other, so we'll get there. And that's the same kind of guarantee we're gonna get in the rest of this talk. And you can do it using only one bit of communication. All right, so agreement is tractable. Now are we done? Well, still no, because this is all in this Bayesian world where the patient comes in with some sort of known common prior. And the challenge with the types of machine learning settings that we're thinking about is it's not necessarily obvious, at least to me, whether or not this should be a good assumption. Right? So in particular, there's a couple things, right? First of all, I don't even know what it means for a human doctor and a computer algorithm to have a shared prior. Even if they were both, machine learning systems, writing down this prior even could be completely intractable, right? Because we have a world where the conditional label expectation could be really complex, right? You've got super high dimensional features. So just writing this prior down could take up way too much computer memory. And even worse than that, updating this posterior distribution could also be very hard. That could be computationally intractable. And finally, we'd really like something that can generalize beyond a one-dimensional prediction setting. And it's not clear how to generalize this result in that setting. And we also haven't shown whether or not we're gonna reach something good. Okay, so the goal here, for the rest of this part of the talk, is can we relax these kinds of assumptions while still maintaining good convergence guarantees, meaning we're gonna agree after a few rounds. And moreover, can we say the thing that you agreed on is going to be good. Okay. Also, for the folks in the back who just came in, there's lots of seats over here. All right. So, as in the previous parts of the talk, though if you weren't there for those parts, it's okay, we're gonna rehash some things. What we're gonna show is that by coming up with some clever conditioning events that we can condition on, we're going to be able to do this. All right. So, what should our goals be? Like I said, the first goal that we want is just some sort of tractable agreement. We want to say that in few rounds with high probability, or for over most rounds, you're going to agree relatively quickly. Okay, so that's what I'll talk about first. And then the second thing we want is we want to say okay, the thing you agreed on was actually the right thing, or the best you could possibly do. Okay. So, instead of this Bayesian setting that I was just mentioning that the related work uses, we are going to do this in an online learning setting. So this is the same setting that Natalie and Aaron talked about earlier, but I'm gonna rehash it here just because now we've got all this like interaction and so we've got sort of like a second dimension, so I wanna be clear about it. Okay, so what's gonna happen? Every day, you could imagine that a new patient walks into the hospital. And for each of these patients, you're gonna have the doctor and the machine learning model converse for some K rounds of communication, where each round they are just making a prediction about what they think, the patient's risk is, let's say. And then they're gonna do this until they agree on some final prediction, let's call it Y hat. And they're gonna do this every single day. So one thing I wanna mention is that the number of rounds it takes for them to agree could be different on different days. So that's like one of the kind of nuances here, right? Like some patients, it could be really simple to make a prediction about. Maybe I just like walk in and I immediately know that they have a 100% chance of getting sepsis because they clearly have sepsis, right? So that's gonna take like one round of communication or even 0. And for other patients, it could be way more complicated. So maybe it takes us longer to agree. And then at the end of the day, we find out, if the prediction object was, did they develop sepsis today or not? We learn what the outcome was. Okay. So time is moving forward with T, and then every day there's K rounds of communication. Oh, sorry, Natalie. Yeah, time moves this way, apparently, according to the slides. All right. So previously, in the earlier parts of the talk, you saw how we can enforce some form of conditional calibration guarantees to get both sort of interpretable probabilities and to make good decisions. So the goal in this part of the talk will be to do the same kind of trick, but with respect to getting fast and good agreement. Okay, so we need to find some conditioning events, but what's like the one object that we can condition on? Well, the only thing that we really have is this full transcript of interactions, right? So you could write down all of the interactions that happen over all of the days, and you could require some kind of calibration condition for different subsets of that transcript. Okay, well, what should those subsets be? Well, we could ask for a couple different things. What's sort of the one thing that you could ask, and you might imagine would be useful, is you could say, okay, for any given round, or like really the thing I want to give a guarantee with respect to is the final thing that we agree on, but that's like a little bit of a wonky object because it could refer to like different rounds of communication. So one thing that I can do to kind of make that easier, right? Like, so I don't have to condition on like round 5 on day 1 when it took 5 rounds of communication, and then maybe on day 2 it only took 1 round of communication to agree. So now we're like having to condition on different rounds and different days, and that's like kind of hard. So, okay, one thing I could do is I could just say for every round, which will include the one where they agreed, I could say I want to be calibrated, conditional on sort of like the full event that describes the entire transcript of interactions before that. So I could say, okay, for like round 4, I want to look at the bucket of all of the days that I predicted 20% chance risk of sepsis, which in this diagram that I have here is like only one event because I only have 3 days on the slide. Then I could say, well, I want it to be calibrated conditional on like, all of the days that I predicted 10% chance in the previous round and 9% in the round before that and 25% in the round before that and so on and so forth. Okay. Like, that would be good. That would be like a super strong calibration guarantee. But if you're a learning theorist, you're just going to say, like, that's way too many events to condition on. Like, I can't do that and generalize well. So even though that would be useful, we can't do it. Okay? So what could we ask instead that's easier? Well, we know there's like only K rounds of communication, or we at least hope, and we hope that thing is like linear or polynomial or something. So you could say, well, I just want to be unbiased on every single round individually, right? I could say, for round K, I'm going to require unbiasedness. And I'll do it like per level set. And there should be a small number of those. So only like I'll look individually at all the days that I predicted 20% and 30% and so on. And I could require that those all be unbiased. And great, this is an object that I can work with. I can generalize. Is it enough to say anything useful? Well, not really. And the problem is it doesn't tell you anything about the collaborative interaction. So we can't really leverage it to say anything about agreement or when agreement's going to be good. But what we can do is instead of just looking at single rounds, really the only important object is to reason about adjacent rounds of communication. So what that would mean is we're going to look at all rounds K and K minus 1 across all days. And if you can guarantee what we're going to call conversation calibration on all of those adjacent rounds, then this will be sufficient to guarantee both agreement, and later I'll show like when it will imply that the agreement is really the thing you've agreed on is like the best it could possibly be. And the reason this is the case is because by doing this simultaneously for all sets of adjacent rounds, it means we are guaranteeing it for rounds 1 and 2, but also rounds 2 and 3, and 3 and 4. So this gives you a way to compare like what happened at round 1 with round 4 because they're sort of linked through this chain of calibration events. Okay. So just to be really precise, we're going to be looking at adjacent rounds of communication, and we're going to require unbiasedness on level sets of predictions that are conditional on both my prediction in round K and also the other agent's prediction in round K minus 1. So for example, we would look at all of the days where the model predicted 20% in round 3, and we're going to subset on just the ones where I predicted 40% in the previous round. And then we're going to require this for all combinations of, K, my prediction, and the other person's predictions. And there's going to be a finite number of these because we're going to sort of bucket all of our predictions to some granularity. So we're going to call this conversation calibration. And in math, this is just a guarantee about the expected bias conditional on this event that I described. Right? So our expected bias, meaning the bias of my prediction in round K, so not the final one, though this will be implied by that, but just in that round is going to be unbiased, conditional on this somewhat complicated, but still not too granular of a conditioning event. I'm going to call that conversation calibration. Okay. Now, why the heck would I want to do this? Well, because it turns out you get fast agreement. So, why is this? Well, if you recall from Natalie's portion of the talk, there was this nice do no harm guarantee that we got from calibration. So in particular, if you have some sequence that's calibrated conditional on another one, then two things essentially must be true. So first of all, if you were able to substantially improve the squared error of your prediction by doing this calibration, then it must be the case that that second sequence, the calibrated one, is different than the first one, right? If I was able to make substantial improvement in my error, I must have changed some of my predictions. Okay? Now, furthermore, since we're in this sort of bounded, we're making real valued prediction, but it's bounded, right? We're making predictions between 0 and 1. And what that means is you can only make this kind of update some number of times, okay? So eventually we're going to hit 0 error. And what that means is at some point, you're going to stop being able to make improvements. And what that, sort of the converse of what I just said about a big drop in squared error, meaning you're making substantial improvement, substantial changes to your model, it means that eventually, when you don't make such a big improvement, you're going to make a very small or no change to your predictions from the previous round. And that means you essentially must agree with the predictions from the previous round. So at a very high level, this is why we can get fast agreement. So we're kind of done with that part of the talk. Of course, I'm shoving a lot of things under the rug. The complexity of this partially comes from the fact that all of our guarantees are actually with a looser notion of calibration called distance to calibration. So there's a lot of asterisks here. But this is how you can get fast agreement. But are we agreeing on anything good? Right? What we really want to say is, like, not only were we able to agree quickly, but like, okay, like agreement could be like a very silly guarantee to give if the thing we are agreeing on is terrible. So we don't want that. So what does it mean for a collaboration process to be worth it? We could mean a couple of different things by this. One of them, sort of the minimal thing that you could guarantee, is that you don't want this collaboration to have hurted either party and expectation. So we get this essentially for free because of these same do no harm guarantees, right? So in particular, if you imagine that the two agents have generated their predictions from some sort of hypothesis classes that only have access to their own features, maybe they started out with some initial hypotheses in this class, then if you compare your final object that you agreed on, its squared error, and the squared error of their initial predictor, you're going to do better because at every round you're improving the squared error by calibrating. Okay. That's great. But can we do better? Well, remember at the very beginning of my portion of the talk, what I suggested is there was an alternate world where the thing we could do, instead of sharing our predictions back and forth, is you could just say, well, like, here's everything that I know about the patient in front of me. I'm going to write it all down, I'm going to send it to you, and then you're going to use that in addition to your information that you have in order to make a prediction about them. And in that world, you could kind of like be doing the best that you could be doing with access to all of the information that everyone had. Right? And that's kind of the strongest benchmark we could compare to. Right? This world where everyone has shared all of their features. And you could imagine that there's some sort of like magical hypothesis class in the sky that we want to compare to, which I'm going to call H sub j for H joint, because it's mapping from the joint feature distributions of both of the parties to a prediction. And you could say, I want to be as good as like the best model in that class on average. Okay? Now, can you do this always? Well, you might be really skeptical. And you might be really skeptical for the kind of following toy example. Right, so in this ideal world, we have this interaction where we're sharing features, and in our world, we have, oops. Hello, clicker. Okay. We are only communicating predictions. But here's an example where this is going to fail. Imagine that the features are generated as follows. The patient walks in and they choose the relevant feature by flipping a coin. So you get one coin flip that's outcome of coin flip that's sent to the computer, and then the outcome of the other coin flip is sent to the doctor. And the patient's true label is generated by taking the XOR of those two things. Now the problem with this is that if you only know the outcome of your coin flip, the best thing that you can do, the conditional label of Y on the outcome of that coin flip, is just 1/2. The best thing you can do is you can guess 1/2. And the same is true for the other party, okay? So what's gonna happen? Well, the doctor would tell the model, well, I guess 1/2, and the model would be like, hey, me too. And so they've just guessed 1/2, which is, essentially also just they're just flipping a coin. And in the world where you have all of the features shared, well, I can if I knew the outcome of both of these coin flips, I could just predict the label. Okay, so there's gonna be some settings where we have no way of competing with this joint hypothesis class. So what can we do? Well, we can at least characterize when we can be competitive. And we're gonna do this using a weak learning kind of guarantee in the boosting style sense of the word weak. We're gonna get there via swap regret, which Natalie talked about and I will remind you of. Okay, so remember swap regret? No? That's okay. So Natalie told you about swap regret in the context of making decisions. So the idea was you're gonna look at your transcript of choices about all of the patients that came over the days, and you're going to say, okay, for all of the times that I predicted that, or I chose that you should take antibiotics, I'm going to make sure that you couldn't swap that out with another action in your collection of actions and get something better. And that's what we called swap regret. Well, here, we're in a bit different of a world. Now we have real valued predictions, but you can kind of do the same thing, right? Particularly, we can bucket all of these predictions, and you can say, well, on all of the days that I predicted like 10%, I'm going to say that we have no swap regret with respect to a hypothesis class. So now instead of like a strategy space of actions, we've got some sort of real valued mapping to hypotheses that you can't swap out for any one of those and improve your squared error. So visually, what does this look like? We're going to look at all of the different subsets of like bucketings of our predictions. So let's say, like, just as an example, the days that we chose 10% as the risk for that patient. And we're going to say that we have no swap regret with respect to a hypothesis class H. If you could take all of those days and you can swap out the predictions for some fixed predictions of a hypothesis in that hypothesis class. And if you can't do that and improve squared error, we'll say you have low swap regret. Okay. Now, could we try to do something similar for these conversations that we're having, these collaborations? Now, we already have a handy-dandy conditioning event in our back pocket from the definition of calibration, conversation calibration, right? So, like, could we do something similar here? And the answer is, well, sure, why not? Right, so again, we're going to look at adjacent rounds of communication, and we're going to predicate on, like, you know, all the times I predicted 20% in this round and you predicted 40% in the previous round, and all such combinations. And we're going to call that if you have low swap regret on those days, meaning if I take my predictions in round K for that bucket, and I swap them out for a hypothesis in my hypothesis class, can I make improvements in squared error? And if the answer is no, then you have no swap regret, no conversation swap regret. Okay. So in math, we're going to look at, say, like the human has low conversation swap regret if for all rounds K and predictions P that they made in that round and then P prime that the other person made in the previous round, then their expected squared error conditioned on that is competitive with the squared error of the best hypothesis in your hypothesis class, conditioned on that same bucketing. All right? Okay. So at this point, you might be feeling sleepy. Why were we doing all of this again? I don't know about you, but when I go to a long talk at this point, I've generally lost the thread. Okay. Why were we doing this? Well, the goal was to say that we are going to be doing well, or as well as possible, in our predictions, right? So one thing you could say that has this strong flavor is you could say, well, you have no swap regret, not only with respect to your own hypothesis class, like that we could kind of get for free using the techniques that Natalie was describing, but moreover, you could ask for swap regret with respect to the union of your hypotheses and the other person's hypotheses. And this is sort of a weird object, right? Because, like, you can't even compute the hypotheses in the other player's hypothesis class because you don't have access to their features. But we could still ask for this. Like, it would be great if we could say it. That would mean that you were doing, in some very strong sense, quite well in your predictions, and that collaboration has, like, kind of helped you. All right, and conversation swap regret is going to get us there. And why is that? Well, because we can ask for both players to have conversation swap regret on their own hypotheses. And moreover, if their hypotheses are closed with respect to constant functions, then this means that they can get conversation calibration. And why is this the case? Well, because if they were not conversation calibrated, then that would mean that they could switch out any of their predictions with the conditional label mean on any of these bucketings and make an improvement in squared error, in which case you wouldn't be conversation calibrated. So What this means is now we've got conversation calibration from low conversation swap regret. And if you're conversation calibrated, what we just said earlier is that you agree, right? And if you agree on your final prediction, well, you know that your prediction has low conversation swap regret and low swap regret with respect to your own hypothesis class. And moreover, the object that you have at the end of this process is something that the other player also knows that they have low swap regret on their own hypothesis class. So you get that for free, even though you can't actually compute any of the hypotheses in their class. So that's great. Again, modulo, a lot of caveats. Oh, great. This is great. This is nice. But the thing I really was talking about at the beginning was I said that we wanted to be competitive with some sort of joint hypothesis class in the sky that has access to everyone's features. So that's not just the union of these two hypothesis classes, because you could imagine there's some sort of complex way that things interact, like in the coin flipping example that I gave earlier. So, right, so we've got this sort of joint hypothesis class that has access to everyone's features, and we want to be competitive with it. But we only have access to our own features. And the final result that I'm going to talk about is a weak learning condition on my hypothesis class and the other player's hypothesis class, such that if we have low conversation swap regret with respect to our classes, then it implies that you're competitive in terms of external regret, general regret, on the joint hypothesis class, meaning your squared error is competitive with the sort of the best squared error in that class, more or less. So I'm not going to talk about this a ton because I want to make sure we have time to go over some other stuff at the very end, but essentially what this weak learning guarantee is, and this is weak learning in the sense of boosting, right? So if you remember back to your machine learning classes, we have a boosting algorithm for classification, and we say oh, this thing will perform very well if you can do marginally better on any distribution than random guessing. And then we take all these weak learners and we combine them to get a strong learner, and we say that thing is going to be close to Bayes optimal. So it's sort of the same kind of idea here, but we're doing real valued prediction. And we're going to say, well, instead of competing competitive with the Bayes optimal predictor, we're going to be competitive with the best model in your joint hypothesis class if any time there is a model in that joint hypothesis class that can make an improvement on a constant predictor, then you must have some model in one of the two players' hypothesis classes that can also make an improvement on a constant predictor. And the way, as a side note, that we get this kind of constant predictor flavor really comes from the idea of calibration, because it comes from this idea that you want to be able to swap out any predictor, constant valued predictor, and make an improvement that underlies a lot of our calibration guarantees. All right. So putting this all together, what we're saying is that if your hypothesis class can satisfy this, or your two hypothesis classes can satisfy this, then enforcing low conversation swap regret implies you're competitive with the joint. So now we have gotten both agreement and we've said you're agreeing on something good. Awesome. And through this, and what Aaron and Natalie were saying earlier, we've seen all of these different contexts where just building a relatively simple set of events to be calibrated on can get us interesting and cool guarantees with respect to our bespoke context. All right. And of course, there's a lot of other contexts that you could also imagine this being useful for, and there's lots of other forms of calibration, which Aaron is going to talk very briefly about.
Almost there. So, yeah, thank you all for making it this far. This is a tutorial, but we only have 2 hours and change, so there's a lot of stuff we didn't cover. And what I want to do just in the last, 5 minutes before opening it up for questions is just kind of give you some guidance to the literature. And on the tutorial website, which will flash on the screen at the end, we've got an annotated bibliography with all of these files. Just give you sort of a, some signposting for what else is out there. So, first of all, as I sort of said at the beginning, there's a lot of different ways to measure calibration error. And what I told you about at the beginning was mostly sort of the standard method, the sort of expected calibration error, which has some nice properties. As we saw, it's really closely tied to decision making. But it's got some other properties that are less nice. One of them is that, like, because it relies so heavily on conditioning on level sets, it's a very discontinuous measure. If I take my predictor and I wiggle its predictions around a little bit, it might go from being perfectly calibrated to completely uncalibrated. And for the same reason, it's really difficult, in the worst case at least, to even measure the calibration error of a predictor. And so there's a whole literature that tries to develop other calibration metrics that still have some of the nice properties of expected calibration error. Maybe there should be some relationship to calibration and decision making, for example, but tries to improve on these other aspects. Maybe you should be able to obtain it online at better rates. Maybe you should be able to measure it on arbitrary predictors with low sample complexity. And so, don't worry that maybe these papers aren't super legible on the slide. They're all on the website. There's also sort of, this other view of calibration. The way we were using it today was we were saying, well, look, it's really hard to learn individual probabilities, so we're not going to try to do that. We're going to try to do this weaker thing instead, where we learn numbers that are sort of good enough stand-ins for probabilities for everything that we're trying to do. But you could also imagine that we think there's someone out there who really does know the data generating process, really knows probabilities, and maybe they're just trying to stay employed as a weather forecaster, and we're trying to test if they're doing their job. Well, it turns out that if I test them by just measuring their expected calibration error and firing them if it's too high, then there are ways to game the system, in that their best strategy might not be to honestly tell me the true probabilities. You might be able to get better calibration error than that. And there's a literature that tries to design calibration metrics that solve this problem, that incentivize truth-telling rather than giving ways to game the system. We also mostly focused on the one-dimensional prediction setting, the setting where the thing that we were predicting was a probability. But of course, very frequently the things that we care about are not one-dimensional objects, they're high-dimensional objects. And the algorithmic ideas we talked about, they all generalize very well to d-dimensional predictions. What turns out to matter is just the number of tests, right? You can sort of handle any reasonably sized collection of tests, even if the prediction space is very high dimensional. And so you can read about sort of algorithms for these higher dimensional settings. Generally the key trick is to make them efficient, in the sense that you want to, even if you have a very large collection of tests, reduce the algorithmic problem you want to solve to just some learning problem over those collections of tests. And, we phrased a lot of the algorithmic discussion here as interacting with an adversary. You want to do well even in the worst case, in which the world is sort of conspiring against you and an adversary is giving you the worst possible sequence. And there's a lot to be said for that. It's great that you can do well against adversaries, but oftentimes that's a pessimistic view of the world. Oftentimes the world is well behaved, has regularities in various ways. You're not interacting with an adversary. And good news, it's possible to do better in those settings. You can give calibration algorithms that kind of go beyond the worst case. If the world is adversarial, they'll recover the sort of worst case bounds I showed you today. But in the event that the world is, nicely behaved, there is a distribution, you can do better. We also sort of, when we talked about the groups with which you're multi-calibrated with respect to, even just describing them as groups makes them sound, binary. Every example is in a group or not. But the techniques we talked about actually sort of don't rely on having these binary groups. They could sort of, these groups could be sort of arbitrary weighting functions. Okay, so multi-calibration more generally just asks that your predictor be calibrated not just overall, but on many different reweightings of the data set. Now, one place that reweightings come in is in distribution shift. Right, like suppose I've got like two distributions that have the same conditional label distribution. Like, if I see a patient come in with some set of features, the probability they develop sepsis will be the same in your hospital as in mine. But like our two hospitals see very different distributions on patients. Well, one way to try to handle that problem classically is to try to learn like the likelihood ratios that relate the distribution on patients in my hospital to the one in yours. And then maybe I could like reweight the data in my distribution according to these likelihood ratios to try to do well in your hospital. The problem with that is I would need a different reweighting for every target distribution, for every hospital in which I wanted to deploy my sepsis predictor. Now, you can note that multi-calibration is kind of requiring that you do well on every reweighting in some collection. And so if I have some family of functions that I believe contains the likelihood ratios for many, between my source distribution and many target distributions, I can learn one predictor, a multi-calibrated predictor with respect to those likelihood ratios. And this gives me a certificate of robustness to distribution shift. I can now take my predictor and deploy it in any other prediction setting in which the target distribution differs from mine under one of these likelihood ratio reweightings. And my predictor is now automatically endowed with robustness to these distribution shifts. And there's a whole literature studying this. It turns out, and we saw hints of this today, but you can really pull on this string, that multi-calibration and these related outcome indistinguishability guarantees are really tightly related to boosting. And not only are they related to boosting in the algorithmic sense, multi-calibration algorithms produce predictors that are sort of more accurate than any of the things that they're multi-calibrated with respect to. They're related to boosting in this dual sense. So if you've taken a complexity theory course, you might have heard about hardcore sets. These are kind of like the dual objects to like a boosting algorithm. And you can draw connections between multi-calibration and hardcore sets and derive new theorems in complexity theory. And finally, like everything we talked about today was about means. We were asking that your predictor be unbiased, subject to some collection of tests, right? Like we're asking for conditional unbiasedness. This is fundamentally about the mean of what you're predicting. It's the only statistic if the outcomes are binary, but more generally, like for different distributions, there's lots of statistics you could ask for about the distribution beyond the mean, right? Like telling me the mean doesn't tell me what the quantiles are, for example. And you can talk about calibration and multi-calibration not just for means, but for lots of other distributional statistics. Anything it turns out that is an M estimator, but in particular for quantiles. And for quantiles, multi-calibration of quantiles is actually quite useful for uncertainty quantification, and in particular conformal prediction, if you've heard about that. The idea of conformal prediction is to produce prediction sets that contain the target label with some given probability. And if you sort of go through the exercise of producing conformal prediction algorithms that are quantile multi-calibrated with respect to some collection of groupings, what you do is you enrich the usual guarantee of conformal prediction beyond what's called marginal coverage to group conditional coverage. Okay, so there's a literature on this, but this is all to say that like there's nothing inherently about means for what we've been talking about today. If you care about some other statistic about your distribution, you can give the same kind of conditional guarantees with respect to many other statistics. All right, and with that, let me thank my co-presenters and open the floor for questions. And I think if there are any questions, there are 2 microphones in the back that will enable everyone to hear you.
Hi, thanks for the tutorial. I have a question about Ira's part, about the conversational calibration, et cetera. I'm over here. Hi. You mentioned this hardness result, that this policy for combining the predictions can't only be a function of the two predictions, right? It has to depend on something else. And so I guess I didn't fully follow during your construction here. Like, what does this conversational calibration actually look like in terms of you need to know, it needs to use a lot more information than I think 30%, you think 70%, right? It needs to know, oh yeah, I think 30%, you think 70%, and it's this part of feature space, et cetera, et cetera. So can you actually like do that?
So right, so that's what the weak learning guarantee is giving us a guarantee with respect to. So specifically, it turns out that under this guarantee, you don't need any more than that. So you don't need to be conditioning about something on the other person's feature space, which is important because like, I don't know anything about their feature space, right? So the key is basically that as long as there's one of the two of us who is capable of making an improvement with respect to a constant predictor, then this process will be sort of competitive with the thing in the joint hypothesis class.
But you need to be using your own feature space.
You do need to be using your own features, that's right. So I think this is easiest to see in the offline setting. So if you imagine we're just doing like risk minimization in the offline setting, what this is gonna look like is at every single round, I'm gonna take the predictions that the other person made, and then I'm gonna do risk minimization on each of their level sets independently. And I'm gonna do that risk minimization in a way that gives me no swap regret on my own hypothesis class. And by doing this, so I am doing risk minimization, which, okay, like, you know, does a human actually do risk minimization when they're making predictions? Maybe not. Or, I don't know, depends on who you are. But that's sort of the trick. And it's because, and then at the end of that process, if I haven't improved squared error, I'm gonna swap out my predictions from the beginning with the other person's predictions. And so that's sort of the key insights that lets us learn something from the other person's predictions, even though we don't have access to their features. I should say also, I think Kenny is maybe still in the audience, so if you've got questions about like the specific no free lunch theorem, I think he's here.
Thank you.
Oh yeah, he's right in the back, he's a little behind you.
One quick bit of intuition is just that adding more than one round helps a lot. Like what's really going on is it's letting me change my mind after seeing what you think. That's what gets beyond it.
Okay. Hello. What would be the clean characterization of the individual probability problem and the marginal estimation failure? Because I think it is the core of a core mechanism, maybe the granularity of the conditioning event and the effective sample size. So would that be the clean characterization?
So are you saying, you know, in our framework, how does one define individual probability prediction?
No, the problem of individual probability, because we said we cannot estimate the individual probability, but theoretically with infinite samples, we could learn individual probability by, for example, negative loss. So I think it may be related to finite sample and the conditioning event granularity, because if the conditioning event is more granular, say its limit is the single sample, so single individual probability. So I think that may be the core mechanism.
So even with sort of, even in the infinite sample limit, if there's also infinitely many contexts, if there's infinitely many people out there, you might still not be able to learn individual probabilities. To learn individual probabilities, you'd really need to see the exact same feature over and over and over again. So like maybe some intuition for what's happening here is that the one thing we can do from data, like the one thing we can measure from data essentially, is averages over sufficiently large groups that we've got enough data to see multiple members of those groups. Now, you'd recover sort of individual probabilities if you could really be, say, multi-calibrated with respect to all possible groups, including the singleton ones. And say I've got like a feature space that's got like n different kinds of observations I could see. There's 2 to the n different groups, and what you see from like the sample complexity bounds we get, where we sort of depend on log the number of tests over epsilon squared, is you can go almost up until that limit and get non-trivial guarantees. But if you really try to get individual probabilities, if you really try to get all 2 to the n groups, that's exactly when these sort of bounds start getting trivial guarantees. So you can think about multi-calibration as some sort of parameterized set of tests that let you dial all the way from at the one end, just marginal calibration, this really weak guarantee that lets you, for example, just predict the mean on everything, to on the other end, that you can't quite reach, learning individual probabilities, which is the same thing as being multi-calibrated with respect to all possible groups. You can't quite get there, but you can sort of get anything in the intermediate region.
All right, thank you for the answer.
Okay, hello. I am solving the problem of reducing expected calibration error in medical object detection. So I understand that in model calibration, there is a trade-off where improving expected calibration error leads to a drop in accuracy and vice versa. What do you think is the key to resolving this trade-off?
Can you say again, it leads to a drop in what?
Accuracy.
Increasing multi-calibration.
Yes, denoising accuracy.
So you're saying like there is a tight connection between, like when you improve multi-calibration error, you increase accuracy, right? Is that what you're saying?
Yes, right.
Okay, so just to make sure I understand, so like in general, the nice thing about calibration is asking for calibration or multi-calibration conditions only makes the predictions more accurate. It improves them, it doesn't make them worse. And one intuition for that is that one way you could be calibrated according, subject to all possible groupings of the data would be to predict the true probabilities. The true probabilities would be the ones that universally minimize squared error or any other proper scoring rule. And so, what these algorithms are doing is when they take a predictor and then try to calibrate it, they're kind of looking for regions, groupings on which the predictor at the moment is doing badly because it's miscalibrated. It's got statistical bias, and it's fixing those regions. And fixing bias only, is accuracy improving, right? And maybe like a cartoon way of thinking about it is that you've got some set of predictors as I start layering on more and more calibration constraints that satisfy all of those constraints. As I add more, I'm eliminating some of the predictors, but I never eliminate perfect predictions. So I'm sort of like narrowing in on perfect predictions as I add more and more constraints, which is why there's no trade-off here. You don't have to settle for worse accuracy by asking for better calibration.
Thank you.
Thanks for handing out your slides, by the way, very handy. I just want to ask, how does what you're presenting here relate to what, years ago might have been called a Bayesian approach to decision theory?
So one way to think about some of these things, and in fact, sort of what's going on very specifically in the part of the talk Ira gave, is that we're sort of replacing Bayesian assumptions with much weaker frequentist assumptions and sort of getting the same guarantees. So one way to think about, a properly specified Bayesian when they condition on features and then make decisions as a function of their posterior beliefs, they are acting according to real probabilities. And if you know a correct prior and you have sufficient, computational power to form posteriors, that's great. Like, posterior beliefs are good for all sorts of downstream tasks exactly because they're real probabilities. But for the same reason, it's really hard to do. Like, this sort of, the only way you can get around this like reference class problem by sort of claiming to be a Bayesian is if you are also claiming to have sort of a correctly specified prior and are correctly doing all of the updates. And so one way to think about this entire set of results is by sort of saying, okay, like, I wish I were a Bayesian, that would be great, but I'm worried I'm not. This is sort of a tractable relaxation of Bayesian decision theory that you can sort of execute without any unrealistic assumptions. So Ullmann's agreement theorem is originally about Bayesians, right? People who are communicating real probabilities. And what Ira told us about was how you can remove the assumption that these are Bayesians, which in general is both sort of computationally and epistemically implausible, and instead just replace it with like a handful of simple bias conditions that you can just check and enforce from data.
And like specifically in the collaboration setting, if you really prefer to be a Bayesian, we have a section in the paper where we sort of lift all of our results back to that setting.
Right, Bayesians satisfy all of these constraints. This is only weaker.
Thank you very much. I just wanted to ask a clarifying question about the first major proof of your tutorial, the one about being an epsilon outcome indistinguishable. So just after you introduced the theorem, you had the slide on this working in the adversarial setting, where you say, so to quote, in rounds, learner observes context, produces a prediction, and then observes an outcome Y chosen by an adaptive adversary. So I don't quite understand what's the freedom that the adversary has in selecting that outcome? Because I presume at the very least, the conditional mean of the outcome given the covariate X has to be fixed, right?
That's right, yes. So one thing that we sort of glossed over is that the predictor may need to randomize, and the adversary can know everything that happened up until that point, and therefore will know the distribution that the predictor is going to sample their prediction from, but does not know the realization. So this is kind of like saying in rock, paper, scissors, you're allowed to know that I'm going to randomize between like rock and paper and scissors at the time that I announce, but if I tell you I'm going to play rock, I'm kind of screwed. Same thing here. So the predictor is allowed to randomize, and the adversary knows everything except the realized randomness for that round.
Well, but does this mean that the adversary can adjust the conditional distribution of the outcome given the covariate as the game goes on? Like it
yes,
sounds
absolutely.
super tricky.
Yes, yeah. It's amazing you can do anything in this setting. The adversary can observe the covariates today. They can observe everything that's happened at prior rounds, and they know what algorithm you're playing. So in particular, they know the distribution over predictions that you're going to make, and they can choose the outcome and the covariates as a function of that. And still, this argument establishes that you can do well.
Like, the only thing they don't know is the realization of every random bits. And the core about how this whole trick works really goes back to the minimax theorem. Like, it turns out that if you're allowed to randomize, then there are ways that you can, even if the adversary knows the exact distribution you're randomizing over, there are ways to pick distributions where it's fine that you went first. It's just as good as if you'd gone second.
Thank you.
Hey, I wanted to first thank you so much for that talk. I work for Kalshi, which is the prediction market you did not mention. We think about calibration a lot, and I think my question to you, broadly put, is, when we run our calibration exercises, we find that, broadly speaking, our error is very, very low. But I'm worried that we might be thinking about calibration in the wrong way. So as it applies to that prediction market context, how would you say that we should be thinking about calibration?
Sure, I can go. So like, the existence of these calibration algorithms that sort of work in the worst case is kind of a two-way street. Like, on the one hand, it's great, and you can obtain, all of the useful things that we talked about here. But on the other hand, it means that, like, if the only thing you're doing is testing whether my predictions are calibrated, in the long run at least, if I participate in many prediction markets, I can pass the calibration test without actually adding any useful information to the market. I don't need to know anything, to pass the calibration test. And so, this minimax argument kind of says, in some sense, that's unavoidable. But it also means that, like why do you want to pass calibration tests? It's kind of like a unit test. Like real probabilities. You're trying to get your hands on real probabilities. Those would pass the calibration tests. So if you're badly calibrated, that's no good. But at the same time, like, you can pass the calibration tests in sort of uninformative ways. At a high level, one takeaway of this line of work is that you can start layering on like more demanding tests that still have this property. I can ask more than just calibration. I can ask for calibration conditional on various things. Maybe I want to be calibrated overall, but also on various different subsets of the prediction markets you've got running, that are segmented in different ways. You should pass those too, right? You can sort of make these calibration tests more and more difficult to pass, and this is zeroing, there are fewer and fewer ways to pass them other than predicting real probabilities as you layer those things on.
I guess like another interesting thing about the prediction market context is that in a sense, this, from like a normative, I guess, setting, like this, some of these settings are like kind of performative and what I mean by performative is like in the sense of performative prediction, right? Where like the thing being predicted is somehow like affecting the true outcome. And there is some very like ongoing and active research in the context of like trying to think about those kinds of settings with calibration, and that's sort of one, I think, interesting thing to think about here. I think Natalie is.
Yeah, I'm actually curious. So you said that, when you think about calibration, you measure calibration, you're saying that the calibration error is low. So what are you measuring? You're looking at the average calibration error of different participants in your market?
So basically you can think about like if you take our markets across different categories and you segment them by categories. So say you have elections and politics and economics and all of those kinds of things. And then you timestamp them at different intervals prior to the result being known, right? So economics is probably the best category to talk about because the markets close a minute before the macroeconomic print happens, right? So you can look a week out to match consensus, or 2 months out or 3 months out, and see how close what the market implied estimate is to the actual realized outcome. And given that the platform has now run since 2021, you have like a reasonable back history, right? It's difficult because in the example that you just mentioned, Ira, like it is true that there are questions around elections, for instance, right? And how informative calibration is, or how much, the market implied probability does or does not influence the eventual outcome. Like we haven't seen that be the result on our end, but of course you're right that there is active research there. So broadly speaking, we're looking at, what the average calibration error is at those different timestamps by category and then overall as well.
That's interesting. I mean, I think that's like personally something I'm very interested in about information markets is the information asymmetries that can arise, and the fact that like naturally, like people know more than other people. And so I don't know how much you have data about, okay, like there's some, you can look at like different subsets of people participating in the market and say, okay, if we're coming up with predictions that are just a function of this group of people, how much calibrated is it versus this group? And how does that correlate with their earnings in the market? To me, that seems really interesting.
Yeah, we could do that. I mean, we're a financial exchange, so we have to collect all of that information. Yeah. Cool. Thank you.
Thank you all so much for your questions. I guess if there's no other questions, then we can all have a good time and stop sitting here.
Let's do it.
Yeah.
All right, thanks everyone.